Hello everyone. So today we're going to talk about diodes and how to use them in logic circuits, but before we do that, here's a funny picture of an otter working with diodes. Well, hello everyone. So today we're going to talk about diodes and the use of diodes for to make just real simple logic gates, which is pretty neat because if you don't have an IC chip laying around, you can just use some diodes in a pinch. I was going to show you what a diode looks like just physically. These are really big diodes here. These are, let's see, what are these? These are 1N540 diodes. These are just, the bigger they are, the more power they can handle, the more current. And here's an example of the small ones here, smaller ones here. But I wanted to use the big diodes here just so you can see them better on camera. But notice there's a little, like a band right here. See that band right there? That's the cathode part. So the way it would look, I'll just kind of set that right there so you can kind of see it. But so the way it would look, the way I have these laying here right now, so the electronic symbol is this. And these are called rectifier diodes. So that little band right here on the diode is this part. So this is the cathode. Here's the anode. And these are important, like resistors, we don't worry about biasing or anything. You can put them in either direction. But these are biased, so this would be positive and negative right there. And so the way it works is you would have like a diode in a circuit like this. And let's say you just have 5 volts. And, plus minus. And let me just kind of draw it this way. Actually, I should have put the 5 volts out here, but you get it. It's, plus minus 5 volts. And let's say you had a resistor, and let's say you had a light emitting diode here. And we've already covered this in previous videos. If you're curious what a light LED is, I've got a video covering that. So this one doesn't emit light. What this one does is, the way it's set up right here, it's set up forward biased. So it's just set up to where it'll allow current to flow and light up the LED. Notice we have a resistor R1 protecting this LED because, and this is all discovered talked about in the previous videos that we have. So the way this works is this should light up. And you have to have, usually most diodes is for them to conduct, they at least have to have 0.7 volts. That's forward bias. Voltage. So, you can't just, oops, that's an L. Pretend that's an L. So that's 0.7 volts forward bias voltage. In other words, I have to have a little more than 0.7 volts, or at least 0.7 volts, I think it is, to turn this on to make it go forward. So in this case, this would already be 5 volts minus 0.7 volts right here, because some of the voltage has to be used to turn this diode on. So that's just one of the little things to keep in mind. And also diodes can be used, and we'll talk about it maybe in another video, where diodes can be used to help. Well, you can build a diode, use diodes in a circuit to convert alternating current to direct current. So that's why we call them rectify. They actually rectify the signal, an alternating signal. And with use of other like capacitors and so forth, you can build a little power supply where you can take AC voltage and turn it into DC voltage. And that's how you're, like when you have a charger, for your phone or whatever, it's usually, you plug it in the wall, it's usually taking an AC input and turning it into whatever we want as far as DC goes. So we can take an AC input of 115 volts and turn, with the use of transformers and capacitors and diodes, we can convert it over to DC, to a solid state DC value like 5 volts or whatever we want. So that's a pretty interesting used for diodes, but also diodes can be used as logic gates. Before we get into that though, but oh yeah, to let you know too, diodes operate as a one-way valve. So like for example, and we'll use the water analogy again. So let's say this is a pipe, kind of a corrugated pipe the way I'm drawing it, but this is a pipe. Okay, and let's say we have water flowing this from left to right, going in this direction. So just pretend a diode is like a little valve. So let's say that this is a little hinge here, and this is a little valve that opens, and this is a little stop for it. So as long as water is flowing this way, you can see it's pushing the little valve open. All right. And so this is water. Just pretend, and so this is the same as electricity, really. So electricity is flowing this way, right? No, it's not impeded at all. And you have to have 0.7 volts to open that little valve up. So it's like you got to have a little bit of force initially to kind of open that valve up, right? Just a little bit, and it'll pop open. That's what that 0.7 volts is. But let's say, so this is forward bias. But let's say you have the opposite situation. So here's your pipe again, right here. And let's say we have our little, this is just a little stop, to keep the valve from going this way. So let's say we have water going this way. And it's shooting, or it's trying to shoot through there. But what's going to happen is the force of that water is going to push that little door down. If you're real mechanically inclined, you'll see what I'm talking about. But so water's coming in this way, and it's going to really push against that. And so now there's no water flow here at all. And so the water's just going to stay backed up. So that's what a diode. So this in this case it would be like this. So you'd have positive. It'd be forward biased, right? Let's just say we have 5 volts here. We have that in there. We have the resistor going. So in this case, current's going to flow just like that, right? But in this case, and this will kind of make sense a little bit when we start playing with making logic circuits out of it. I don't know why I'm drawing my power supply the way I'm doing it, but so this way we're going to reverse bias it. Yeah, this is called reverse. I need to say reverse bias. I didn't write that down. So this is reverse bias, right? So now you can see we've got it in reverse, right? We got the diode in there, and usually that's not a good thing for some components to have them reversed, but diodes are kind of made to work that way. So now, see, this is the cathode, this is the negative side, and the positive side for this. So notice how now current is trying to flow, but boom, it hits that it's reverse bias. So now the diode is resisting the current flow. So now what you have is it's acting like an open. So really you would measure about 5 volts right here, because it's really acting, it's preventing, it's just as if you broke that wire now and no current is flowing through here at all. So there's no current right here at all, flowing or here, right? So it's just stopped right there. So it's actually, essentially it's looking like this. Let's see if I can draw it a little better. I'll try to draw my symbol the correct way. So really it's looking like this. It's acting like a switch, kind of open, right? Maybe that was a better way to draw it over there too. I'll do that here in a minute. But so now it's kind of acting like this. So therefore, it's not going to flow. No current's going to flow here. It's just nothing. So it's acting like an open. And so the same way with this one, it would be like this. So in this case, if we had a switch here, then it would be, that's kind of what a switch looks like on sort of, in circuit, in schematics. So now, current can flow like that, right? So that's really what we're dealing with. So really it's just a switch. It's either on or off, and on or off. So a diode can be a diode can be on, or a diode can be off. Like we can look at it that way. It's just it's like a switch, right? On or off. You know, even you can do switches with. So this is binary. That's equal to a 1, and that's equal to 0. So this is really binary if you think about it. Or it could be, you could call it, a diode could be, let's say we have this 5-volt supply here. Well, a diode could be 5 volts. You know, it could be on, right? Or we could have, you know, or it could be 0 depending on, well, actually this isn't the most accurate because it depends like how we have it set up in the circuit. But let's say we wanted the diode, if it's on, to equal 5 volts and off equals 0 volts then. But you'll see what I mean when we start playing around with some of these circuits. So, okay, my apologies. I was running out of room. I was running out of real estate on my paper, so I decided to go with another new piece of paper. So, continuing our little chat here. So, you know, as we said here, so really a diode is just really a switch on and off, and we can do a lot with that. We can make decisions, like we can build logic gates, and that's how computers work. It's really all about just switches going off and on, but they're very tiny, tiny switches, and of course it gets very complicated. But in a real kind of gave you an understanding, you know, we can create a diode, we can use diodes as logic gates. And so we're not really using them here to rectify anything. We're just using them as switches. So you can use them to rectify things, you know, waveforms and stuff. But here we're just using them as an on-off kind of thing. So really, we'll go over one concept. So let's create an OR gate. So this is just something you have to kind of know. This is digital electronics. You know we have binary as 0 and 1s. So we can create a truth table. This is a truth table. And what's great about truth tables is, let's say I have a 2 input. Let's just draw input A, input B, and we have a diode here, and one here. So now we can put these together, and let's say we do something just real simple like this, and here's our output. We'll call it O. We'll call it O. And let's say we have, you know, let's say 5 volts equals to on and 0 volts equals to off. Okay, so this is going to be an OR gate. And this is just one of those things you just have to kind of remember. Usually I like to try to come up with cool ways to remember things, but really, so a truth table will look like this. You'll have inputs A and B. This is your input side. Right, so we just have those 2 inputs right here, and then A and B, and then we have an output side. Right, and we'll call it O right here. Right, there's your output. So what's cool about truth tables is, I mean, and you can really do a whole lot with truth tables, and there's a whole lot of other videos I plan on doing about. You can use Boolean logic, you can use Karnaugh maps, all kinds of cool ways of just, I mean, you literally can take the output. Let's say I was measuring some circuit and I've measured all the outputs. You can generate the inputs from that, or if you had the inputs, you can generate the outputs, and you can figure out what gates are being used. So it really gets really fascinating. It gets a little, it almost becomes like a game, because Karnaugh maps are a real visual way of reducing electronic components in a circuit. So that's very powerful. So you can take a real complex circuit and sometimes reduce it down to real simple logic. But so a truth table, like notice I have 2 inputs here. Well, I only have these combinations. I can have a 0, we'll say, you know, 0 volts. Let's say this is 0 volts. So I could have 0 volts on here, right? Or I could have a 0 volts here and 1 volt there, right? Or I could have 1 volt here and 0 volts there. Or I could have 1 volt here and 1 volt here. Okay, so I've got 4 different combinations here, which is because and the reason it works out that way, it's because I only have two inputs. So and you know, not to get too much math involved, you know, binary is based on and this is something I'm definitely going to cover in a different thing, but like you can have 2 to the 0 power, 2 to the 1 power, 2 to the 2 power, 2 to the 3 power, and we won't go much further than this, but 2 to the 0 power is 1, 2 to the 1 power is 2, 2 to the second power is 4, and 2 to the third power is 8. So this is binary, and this is decimal. So what we're doing, well, that's an 8, not a 3. So what we're doing is we're just converting binary to decimal here. But really, you know, we only have two inputs, right, and one output. So really, you know, we have 4. So I guess what I was trying to say is we have 2 to the second power. So it's 2 to the second power here of combinations. So we have 4 different combinations that we could do. So for an OR gate, the OR gate is just set up to where if I have 2 zeros or 2 lows, in this case, I would have 0, right? 0 volts. If I have a 0 here and a 1 here, then I have 1 volt. That could also equal to low, and that could equal to high. Call it that way. And then the same here. If I have a 1 on A and a 1 on B, then you know, I'd have 1 volt as well. And then if I had a 1 and a 1 here, then, you know, I would have the same thing. So this is an OR gate. I noticed on my truth table, really, most of the time, I think I just kind of made a typo, but it's usually 0, 0. Oh no, that's right. Never mind. I thought I had transposed these. No, I think that's correct. Yeah, 0, 0, 0, 1, 1, 0. That's right. Never mind. I thought I'd made a mistake, but I didn't. So we'll forget that. Sometimes I'll see things, I'll think, oh, wait a minute, I made a mistake, but it turns out it's okay. It's 0, 0, 0, 1, 1, 0. Because really, if you look at it, this is decimal 0, this is decimal 1, and then decimal 2, and then, you know, that way. So anyway, so kind of, you know, and this is really this is this is decimal 0, decimal 1, decimal 2, and decimal 3. Because you got to remember we're counting from 0, right? That's why it doesn't say 4 here, but it's 4 different combinations. So just remember that and forget this. I thought I had wrote something in wrong, but it's correct. So anyway, so this is an OR gate, and that's the truth table for it. So if you think about it, up here, if you look at this OR gate, you'll see, and you notice my notes get messy because I'm doing this real time. I'm not, you know, this isn't like pre-planned, so that's why I bumble around and make mistakes. But I feel like that's realistic because, you know, everybody's that way, you know. But I try not to waste too much time in the videos on making mistakes. But sometimes if I'm making too many, I just stop and start over. But anyway, so to kind of give an idea, though, of how this is working, if I put 0 volts here, well, I have to have I need at least 0.7 volts for forward bias. So in this case, well, I don't even have that. So this diode just won't turn on. And if I have a 0 here, the diode won't turn on either, right? So there's nothing to pass. So therefore, this one would be 0 volts. So that'd be 0 volts. If I put in a 1 here, oh, let's see, how did I have it? Oh, say, so this is A and B, right? So if I do a 0 volts at A and 1 volt at B, then, and I have a diode here, then I'm going to have 1 volt, right? So you can see I'm starting to, like, so this is output, the first output, 0 volts, had zeros. Now I'm doing a 0, 1. Well, I got 1 volt because the current's going to flow right through there. Because we have that 0.7 volts. You'd probably measure like, I don't know, 0.93 volts or something, maybe. Something like that. So, because, you know, here, so we're getting an output. The same way with this one here, we got, so now A is 1, right? And B is going to be 0. So we'd have this guy. Oh, well, you have a diode coming in here. This is horrible drawing. Anyway, but I think you're getting the idea. Like, so now if I got 1 volt on A and 0, well, current's going to flow this way. I mean, nothing's going to happen here, but current's going to flow this way, and we're going to have 1 volt, you know, approximately 0.93 volts, I think. And it's not a perfect world, right? So it may be off a little bit, but then of course here it's the same way. You know, now we're going to have, you know, A and B. We're going to have 1 volt, 1 volt. And this, oh, there's my, well, let me draw my diode. Here's my diode. Sorry about that. Actually, I can just color that in. That's how a diode looks anyway. Okay, so there's your diode. And then we have 1 volt. And the reason being, now current can flow this way, you know, it can go this way. And of course, it'll combine, right? And it'll come out here. It'll go that way. And then here we got nothing. so you can see, if you look here, and this was the output, right, for all these. Well, now you look at my truth table. Well, my output was 0, 1, 1, 1. So that's the truth table for an OR gate, and that's how you can use logic. I mean, these diodes as logic gates, or logic switches to make logic gates, which is really pretty cool. And normally that you wouldn't do that unnecessarily. I mean, you know, you could, but I mean, we have transistors we can use, and we have actual. Oh, and actually, the symbol for an OR gate symbol is usually like this. Instead of all this stuff, it's usually really simple. It's like this. This is an OR gate. And I'm doing a horrible job at drawing it, but notice how it's concave here. And you have 2 inputs, A and B, and then you have your output. So if you ever see that, you know, in a circuit, so instead of having that up there, instead of having this thing up here, you'd have that. And you can actually buy chips. You can buy, and I can't remember the number right offhand, but you can actually buy a little circuit IC that has 4 of these OR gates in it. And of course you can buy, you know, bigger ones and everything, but usually I think the minimal is like a 4 OR gate one, and you can do all kinds of cool circuits with that. But I thought it'd be kind of fun just to show diodes being used. I mean, I guess you could use these in a pinch, and maybe they are somewhere used in circuits, but I think normally you would just see like that. You would see like a chip in there. You know, it's more efficient, but it's kind of cool though, just to think about how people probably used these a long time ago. Before they had ICs, they had to use discrete components, and then, you know, transistors came out, and you can do a transistor the same way. A transistor can be a switch, or it can be used to amplify things, but you can have a transistor just turn on and off, kind of like we're doing here. Okay, so that, I think that kind of gives you an idea of how a logic gate works, and you can apply this to different, you know, there's AND gates, OR gates, NAND gates, NOR gates. So I'll draw them out here. So we have OR gates, you know, we have AND gates, NOR gates, and NAND gates. So we have quite a few NAND, that's an N, pretend that's an N, gates. Yeah, so we have all kinds of these little gates, and the symbols look a little different. And so let me get a new piece of paper, and then we'll go over that. Okay, so I ran out of space on my other piece of paper, so I'm trying to, I tend to run out of space and keep putting stuff in there. I'm trying to make it a little clearer. I'm trying to, you know, change paper more often. so you guys can see it. But so let's go over the truth tables for each gate. So, and this will apply to the lab here shortly. So we have, I always like the OR gate for some reason. It's easy to remember, but so we'd have A and B, right? And we know that A and B is 0, 0, 0, 1, 1, 0, and 1, 1. And of course, you know, the output, and this, you know, and remember, you know, 0 can be 0 volts, it could be ground, it can be, you know, even a lower voltage. 1 can be, you know, or it can be off, right? Off, or it can be, you know, 1 can be on, or 5 volts or 9 volts, whatever, or high, you know, something like that. It represents a voltage, right? 0 represents a ground, really. So here you'd have 0, 1, 1, 1. Okay, so that's that truth table. All right, and then we have a thing called a and it looks like this. That's an OR gate. There's your output. Okay, an AND gate. These are the ones I remembered first, so I guess they're just easier for me to remember. The other ones I have to think about a little bit. But you know, when you're using these a lot, you remember it. So don't be overly concerned about memorizing this. If you after you play with it a little bit, it starts making sense in your mind, and you know, you can remember them really easy. So the truth table thankfully doesn't change, because you know, it's always the same combination. It's the outputs that are different. So always remember that. You know, this is always the same. So you already know most of it, right? And so let me put output here, so you don't think that's just a 0. Okay. So here for an AND gate, it would be 0, 0, 0, 1. It's only 1 when you have 2 1s. So that's one way to remember that one. And the OR gate is 0. It's all the time. It's on all the time except for 0. And the AND gate is only on, you know, it's only 1 when you have 2 1s. So so that would be your AND gate. And the AND gate looks like this. Just kind of notice the difference here. That's straight and that's curved. That's really the only difference you got to worry about there. Okay, and this is of course A, and these are inputs here. These are inputs. Oh, all right. Well, let me squiggle that out. Input. Misspelled that. Input. That's the input side. So this part of the truth table represents this, right? This part of the truth table represents that. So same here. So there you go. So now, just to add insult to injury, I suppose, there's and this. So I'll line them up. So we have a NOR gate, and we'll refer back to this here in a minute when we go to the lab. So that's why I'm doing this, and also it helps you just to kind of see all the truth tables. And also remember to go to my website. It's buildcircuitswithrich.com. And if you go out there, I usually scan in my notes, even with all the squigglies in them. And then also, we'll have it better on the website. I have it, you know, laid out better for you. And we'll have all this information out there. That way you don't have to worry about writing things down or trying to remember stuff. Just go to my website, buildcircuitswithrich.com, and you'll see the video and you'll see all the other information on the website there that explains all this. Almost like a transcript, sort of. So remember, input, you know, 0, 0, 0, 1, 1, 0. Now, I could have put 1, 0, 0, 1. It don't really matter. As long as you're covering, I mean, I could really, you know, but if you stay consistent, it's easy to remember the logic, right? That's why, and we're counting in binary. If you think about it, we're going 0, 0. This is 1. That's 2. And that would be a 3 in binary. And 0 through 3 is actually 4 states. Like if you count 0, 0, 1, 2, 3. So it's 4. Okay, so a NOR gate is a little different. A NOR gate is going to, and the reason I wanted to line these up, a NOR gate is the opposite of an OR gate, right? So a NOR gate, so you really, if you want to know it, really, that's why it's easier to just to remember the OR and AND gates, because you can figure out the NOR gate by just saying, okay, NOR means it's opposite of the OR gate. So here I would have, if you just look up here, get this a little better. So if you look right there, all right, all I got to do is invert these. And there you go. So that's a NOR gate. It's just the opposite of an OR gate. That's pretty simple, right? I guess that's probably why in my mind I always remember the OR and AND gates, and then from that I didn't care because I could just say, oh, just take the opposites of those. So just kind of a handy tip there, at least. And then a NAND gate is the same way. It's almost like, it's like not or not and, or I don't know if that's really the way it was meant to be, but that's kind of how I think of it. So hopefully that helps. Okay, so, and again, 0, 0, 0, 1, 1, 0, 1, 1, right? And then, so the NAND gate is just the same. I already have my AND gate, so I'm just going to take the opposite of the outputs of the AND gate, right? Right here, so I'm going to say 1, 1, 1, 0. And there you have it. There's your logic outputs. Oh, and let me, well, really we don't totally have it. I need to draw the symbol. Okay, so the symbol for the NOR gate is really all it is. And if you know what that is, you'll know what this is. So here's a B. Here's B, and of course it's the concave looking thing, and then you have just really we're drawing an OR gate. But before you draw the line, draw a little bubble. That's all you got to do. So, and what that means is, and we'll talk about it a little later, but that little bubble just means an inverter. So really, an inverter is just a little circuit that switches it to the opposite of whatever you had. So if an inverter would look like, I think an inverter is, I think it's like this. So if I have 1 volt here, I would have 0 volts there, right? Or if I have, 0 volts here, I'd have 1 volt there. It just reverses things. So that's what this NOR gate. That's why it's taken the opposite of it. So what's happening is it really looks like this. Right, this is a NOR gate, and then it comes out. You have your inverter, right? So what the way that's working is this is an OR gate now. I kind of drew it kind of like a Star Trek symbol or something. But so let's say I had let's say I had 0 right here for my input. So an OR gate would say 0, 0. I'd have a 0, but see with this guy, it'll invert it and make it a 1. Or if I had a 1 here, it'd be a 0, right? So that's why this is opposite. So if I have 2 zeros, the OR gate's going to be 0, and I'll get a 1, right? And if I had 1 on either one of these, I'd have a 1, and it would turn it to zeros. See, so it's just inverting. So it's got a little. So that's why they call it a NAND gate. It's not. Excuse me. That's why they call it a NOR gate, because it's not OR. If that makes any sense. So, but that's the symbol for the NOR gate. That guy. And I was just trying to explain what that little bubble is. It's just an inverter. So it's an OR gate with an inverter on the end. That's the best way to explain that. And the same way with the NAND gate, it's like this. So a NAND gate is this, right, with the little bubble on it. A, B, and out. So and electronically, if we wanted to break this little guy down a little more, we would have, there's our little inverter, which they just put a bubble on the end, which makes sense because you wouldn't want to draw this weird thing. So you'd have A, B, then here's the output of the AND gate, but it gets inverted. So for an AND gate, anytime I have a 0 here, like all through these, right, they're going to get inverted. Like, see up here I had 0 outputs. So there they are. And then I have, but now I'm inverting them to make them 1, right? Because of that little inverter we have at the end. So that's why it acts the way it does. So really, if you take an OR gate and just take the mirror of it or the opposite of it, then you end up with an OR gate. If you take an AND gate and mirror that and take the opposite of it, you get a NAND gate output. So anyways, I hope that helped. This is just an inverter. Not inventor, inverter. Okay, cool. All right, and what we'll do is we'll look at some of these in the lab. So I think it's time to go to the lab. All right, so we're in the lab. And I thought before we get too far into the lab part, what I wanted to do was show you just a basic diode circuit real quick. So what we're going to have 5 volts. And we're going to draw it. You know, sometimes in other videos I've said that I kind of like to redraw things sometimes like this, because sometimes it's a little easier to understand. So this would be ground. All right. So sometimes it's easier to draw it out like this. You can see it. So here's we'll call this D1. That's just the regular diode. This is the rectifier diode, and then we're going to have R1, and then we're going to have LED1, and so that's how you tell an LED. You got, you know, you've got the little arrows pointing out. That means it's giving off light. And this is just a rectified diode. It doesn't give off light. But the way it is, the way this circuit is, it should light up because current's going to, you know, this is the positive and this is the negative of it. And this is positive and negative, right? So current's going to flow from here. It's going to go through the diode, you know, because it's bigger than 0.7 volts. And so it'll drop like probably 0.7 volts. And then, you know, you have R1. I'm not sure what, you know, I just picked a random resistor. I'm not sure what I have, but it'll go through. And then, of course, then the LED, I've got a red one. It's about a 2 volt one or something. So, you know, I'm just guessing maybe, you know, this might be 2.7 volts, maybe, whatever we put in there. And then it'll go down to ground. So I built the circuit, and never mind I've got like another circuit on the same board that we're going to go through in a minute, but I kind of wanted to, just to keep from confusing you, I'm going to try to move that one over where you're not seeing that, but see how I have it on here, so you can see the circuit. Try to get this up a little better where we can see it. I just didn't want to confuse you with, see, I've got another circuit we'll go over here in a minute, but I didn't want to confuse you by, I just wanted you to focus on this. So this circuit right here is equal to this, right? So current, there's the positive side, it's flowing through the diode. You can see the little negative. So this is the anode, and there's the cathode. It goes through the resistor, it goes through the LED and the ground. So that's what we have. Now, if I take, I'm going to move the circuit out of the way. If I take, I'm going to redraw it again. If I take that diode and put it in reverse bias mode, and this is the power of the diode. There's my LED, LED1. So this would be on, right? Because I'm seeing a light. So this is on. And so this is a D, you know, well, now I've got the negative side up here against the positive side, right? So it should be, so this is D1, and this is R1, and this is the LED. So probably what I'm going to see is this is going to act like an open, and we'll measure like here and here and probably read like an open. So this should be off. There shouldn't be any light, because this diode's reverse bias now, and it's going to be blocking the current. So there shouldn't be any current flow through here. I mean, enough to do anything. So let's take a, I'm going to move it there and get our circuit. Whoops, let me move this over here where we don't confuse anybody. Okay, so, all right, so now what I'm going to do is turn this off, and then I'm going to reverse the diode. And these diodes have ratings, like I think this one's really high. I mean, you can go like to 50 volts on it or something, reverse mode. So that's something to always consider if you're, you know, make sure your diode can, because it's not infinite, right? I mean, you know, if I put 100 volts on this thing, it's going to blow up the diode. It can't handle it. But I think this one's good at 50 for some reason, which is amazing. So I could actually, you know, you can put quite a bit of current through it in a reverse mode where it will block it. So, but they will heat up too, so you got to be careful of that. So let's try to turn this on, and see, I've got nothing. so right now, yeah, I've got 5 volts, and then I've got it reverse bias, so it's blocking it, no current flow. And so let's measure the voltage across here and see what we got. I'm predicting we would have, it'd be like an open So let's see if I can measure that. So across the diode, we'd probably be measuring, see there we got 3.58 volts. So if I measure just the, let's just measure the source, we have 5.04. So it's blocking most of that current across there. So that's pretty cool. And that's probably because of that. So if we measured, let's see here. Well, of course, if you measure here, of course, you're going to read the 5 volts all the way. Well, I guess. Let's see. Oh, I'm on the wrong thing. Okay, 5 volts there. And then let's see what we got across here. I'm just kind of curious. We got nothing. So, all right. So, yeah, we got nothing there. If I measure here, we got 3.59 volts. So yeah, so you can, so you can kind of get an idea that this is acting like an open. And if I flip it around, I'm just going to do it. Normally I don't do this, but since it's, I'm going to do it like it's on a, I did it with the power turned on. So see there, I just flipped it around. Now we're good. All right, so let me move this out of the way. And we're going to move it on. We're going to move on over and see if we can look at a circuit. So let me unplug this guy. And let me turn the power off. We're going to unplug this guy. Get these little components out of the way. And now I'm going to, let's see, I believe this is my OR gate right here. And I'm going to put the power supply on. So, yeah, these little power supplies are really awesome. See how I can put those on. And so what I've done here is built an OR gate circuit. And let me go ahead and draw the schematic real quick, and I'll be right back. Okay, so this is the OR gate, and we've got it all breadboarded, which is great. So you can see the circuit here. Now here's what it looks like, in the schematic. So you can see here I've got, if you just look right here, yeah, you can see here we have 5 volts running to a switch right here, and then we have the D1 here, which is the diode. It's you can see here's the cathode right here. There's the anode, and it's going to a resistor, and then it's going to D3, which is right here, and then D3 is going to ground. So I had to use blue wires here because I didn't have any black wires, but it kind of matches that rail color. So then we have input B. So that was input A. Input B is right here, and you can see we have, we're just, really what we're doing is we're just like you see, here's 5 volts running here. We're just tapping into that same wire really on that side of the switch, and then we're running the 5 volts here. So it's, instead of running it from here to here, I'm just tapping in and running it here. So so here's the switch, and then here's the D2, here's the anode, and then the cathode. You can see the little marker there, the little band, and then it goes to the resistor, and then it goes to the D3, and then it goes to ground. So now these are inputs A and B, and then here's the output. And here's the truth table. So if the light is off, we have a 0, and if the light is on, we have a 1. And you can see here, this matches. This is just lining up with the truth table to let you know 0 is off, 1 is on, 1 is light on, and the other one is light on. So, all right, let's give it a try. So the first one would be, right now, we would have 0, 0, and of course, with the switches up, that means we have 0, 0 because we're tying it to 5 volts. So that would be our high, right? So so that's why the light is off right now, because I haven't pushed the buttons in to turn them high. So this would be 0, 0. So by default, it's set to 0, 0. So let's go with input B. So this is B. So we're going to see if the light comes on. So there it does. It comes on. So that's a 1. And then A is 1. So we want to push down on A. And there we go. The light is coming on, so we got a high. And then if we push both A and B down at the same time, it should light up. So there you go. There's an OR gate. And so just again, with the buttons not pushed, that's by default it's 0, right? 0, 0 equals 0, light off. And then we have B, which is on. We get the light on. A, push that in, light on, and then both buttons, A and B, output is high. All right, so that's great. So now what we'll do is we'll move on to the NOR gate. All right, so now I just went ahead and did the drawing for you, so I don't waste your time watching me draw this circuit. But so what we have now is we actually have the actual circuit. This is a NOR gate using diodes, and so here's the truth table for it. So anytime we have zeros, we'll have a light. Anytime we have ones, we'll have zeros, right? And to do the circuit, or the way the circuit's done here is, so if you notice up here, this is ground, these blue wires, that's the closest I could find. I didn't have black, so I used blue. And of course this is, so the positive rail is the red, and then the ground is blue. But you can see I've got this switch right here connected to ground, right? And then I have the end of the diode on the other side of the switch right here. And you can see this is the negative side, or the negative side. In other words, this is the negative, the cathode, right? There's the anode, and that's positive, and it goes to this resistor network. So I have 5 volts going to the LED, but I have these diodes, if you can see them, they're kind of plugged in there, right? They're kind of hooked in right here. And ultimately what we're doing is, whenever I push one of these switches down, it's going to short across that diode and make it turn off. So what's going to happen is when I put this switch down, the volt instead of, right now the voltage is flowing through here and lighting the LED up. But when I flip the switch, one of the switches on, the current's going to go here, but it's not going to go here because this is a shorter path to ground. Oh, sorry, there's my meter again. I'll go ahead and turn it off. So what I was going to say was, right now current is flowing from 5 volts to the diode and lighting it up. But when we flip one of these switches, current's going to go through this resistor, and it's not going to go here, it's going to go through here because this is an easier path to ground. So current usually flows that way. It usually takes the shortest path. So ultimately what we're doing is we're shorting across this diode and making it turn off. And we'll take a measurement here in a minute. But so here's our circuit, and then here's our truth table. So right now, the switches are up. And you can see the diodes aren't even connected in the circuit. So I've just got, the resistance, the diode, the light emitting diode going to ground. So it's lit up. Now, if I push one of these, it's going to short across that diode and turn it off. So this would be, this right here would be A, B. So A. So if we do, so if we do B first, see how it shortened it across and it turned it off? And I'm looking at the truth table here. So next one would be A is on, B is off. It's going to short across it, right? And so when I do this, current is flowing from here through here, and it's going to ground. When I let off, now current's flowing through here, through the diode to ground. So to give you an idea. And then so B, of course, A is that. And if I turn both of them on, they're both shorting across the diode to ground. So yeah, there you go. There's a NOR gate. So it's 1. So the output should be 1. Then if I do B, it should be 0. If I do push A in, it should be 0. And if I push A and B in, it should be 0. So how cool is that? So now we have a NOR gate. And I'll go ahead and build the NAND, the AND gate, and then we'll see how that works. Okay, so we're going to go over an AND gate, and I'll go ahead and draw the circuit out, I guess. So the way we did it with this one, and it's a little different. I mean, it's we had to kind of make some, since we're only dealing with diodes, we had to kind of make a little bit of little adjustments here. But so here's the switch, and of course to close it, it goes that way. Here's the diode, negative, positive, right? And then here we have a what they call a pull-up resistor. I'll kind of draw it over here because I'm getting over into my area. So we got 5 volts, right? And then this is just a pull-up resistor, R1. And then we have a LED. We'll call it D3 because, we have the other diodes. So it's kind of coming to ground. So right now, you know, these are not doing anything. So right now this is considered, you know, we're considering it 2 1s on here right now. And I'll show you here in a second. It's a little, you know, sometimes using just diodes is a little harder to build a gate, but we'll kind of show you what's going on here. So, but right now, let's just draw this out so we can talk about it. So I'm just going to connect this. All right, then we're going to have that. Got our switch. There's our switch, and this goes to ground. So it's a little different this time. We're going to ground this time. So really, remember that's 0. Ground is 0. And so the way we have it now, it's a pretty simple little circuit. Right now, the way it's set up, we've, you know, since these are grounds, what'll happen is when we put 0 0 on here, these diodes are going to short across the LED. And since, you know, the LED takes about 2 or, I don't know, approximately 2 volts to turn on, well, these only take like 0.7 volts. Right? So what's going to happen is when I flip this to ground, it's going to come here and say, oh, that it takes 2 volts to turn that on. It's going to flip around, and it's going to go through that because it's the easier path to ground is only 0.7 volts. So what's going to happen is when I flip one of these to ground, or both of them to ground, it's going to go this way and go around the diode and turn the diode off. It's going to essentially short across that diode. With it up, then the diode's going to stay on. So with both of these switches up, that's like having 1s on here, if that makes sense. So, I mean, I could take the switches out and run the diodes up here, and the light would still stay on, you know, like the diodes aren't doing anything. So it's kind of electronically, it's kind of a weird thing, but, so let's go ahead and go through it. So right now, this is ground. It's going to the switch, right? And then it's going to the diode, and you can see from the little bands here, this is the cathode, and then you know, there's the anode going to the resistor, and here's 5 volts. Now that blue line rail is the ground, and you can see where I've got ground going up there. So this is the positive. This is the 5 volts. It goes through the diode, goes to ground, and it's lighting up everything. Now when I push this button, so right now we got just consider this a 1 and a 1 because. And like I said, we're using a ground here, so it's a little confusing. But let's just pretend. Let's say I even put this to 5 volts. You know, it's the same potential, so really it's not going to turn anything off. So this would be, we're kind of going backwards, I guess, in a way. So right now we got high on here. Let's just consider it high, meaning that the absence of a 0 means high in this case. So. And what's cool about it, if you have a real AND gate like a IC, you can actually do it better. But so we're just going to consider. My apologies, my meter went off again. So we're going to consider it. This is a high. This is 1 and 1. So we got a high. Kind of smudged my LED there. Now if we go zeros, now by pushing them in, see, I'm going to make this is when I make contact, it's going to bring them both to ground, and it's going to turn it off. Because what I'm doing is I'm shorting across that LED. I'm shorting. It's when I push a button, it goes. The current decides it's not going to turn on the LED. It's going to go around and go to ground every time. So this would be 0 0, and then A. This is A. So A is 0, right? This is still high because, well, we're considering it high. This is B, which is well, I'm going to make it 0. Right, and then again we have 0 0. So it's a little different, this circuit, because we're dealing with diodes and we can't make it, you know, perfectly. Oh, just turn that off completely. That is the cool feature about this Astro AI DM200M. It does beep a lot at you if you not using it. So just pretend right now this is 1 and 1. We get a high, right? 0 0. I mean 0 0. We would get a low output, and then A is low. We get a low output. B is low. We get a low output. So there you go. So that's an AND gate, and now we'll do a NAND gate next. All right, so now we're looking at the NAND gate using just diodes. So again, like the AND gate, it's not going to be as perfect, but if you had a real gate. But so here's the truth table for it. So remember, the NAND gate is just the opposite of an AND gate on the outputs. So, on an AND gate, if you have any zeros, you'd have 0, and you'd have to have both ones to make it 1, but this is the inverse of that. So here's our circuit, and I can't take credit at all for this circuit. This is, I tried to do it myself, but I mean, there's just some things that, there's super smart people out there who figure out things, but, and again, I got this from the Forrest Mims, the third, it's Forrest Mims Engineers Mini Notebooks. And like I said, you can find them out on the Internet Archive, archive.org. So it was really cool. But so I thought, I'm just going to do that. We'll build it and we'll see how it works. And it works great. So what we have is we have 5 volts. You can see up here. I've got R1, which is 1 k ohm. R2 is 1 k ohm going to this LED. And then we have a 4.7 k ohm resistor. That's R3 going to ground. And the way it works is, and of course we have the diodes. Now here's the D1 and D2, and this is D3, of course, is the LED. But there's my switch. It popped loose. So I have these diodes switching over to ground with the switch. You can see the switch here, and then this is the cathode going to ground. So that when I turn it on, the diode's going to be forward biased. Same way with this one. So this is A and B. And so let's power this up. So when it's powered on, we're just going to consider this as 1 and 1, right? So 1 and 1 would be 0. See there? Now when I push these buttons, it's going to short these to ground. So this would be 0, 0, which we get a 1 output. And if A is 0, then we get the output, it goes 1, and if B is 0, then, and we're considering, what we're doing is we're just kind of having to, in our mind, consider when these buttons aren't pushed that it's a high, right? So just think of it, if the button's not pushed, then that's like having a 1 on there. And so that way, so right now, A and B are 0, so you have to push them in to short them to ground. So that means we get a 1, and you can see here on the truth table. And then if you push B in, you get a 1, right there. And if you push A in, you get a 1. And then if you push both of them in, well, actually, if you push both of them in, you get a 1. But if you're not pushing them in at all, that's considered a high. So therefore, we got an output of 0. So pretty amazing little circuit. But that would be a NAND gate. So yeah, and again, I got this. This is inspired from Forrest Mims, the third engineering mini notebook. And what we're going to do is, while I was perusing that, I noticed there was a decimal to binary encoder using diodes, and I think we'll do that next for the next video. So yeah. So thanks again for hanging out with me and going over diodes and diode logic, and we'll see you next time. And we appreciate it. Thank you. Well, thanks everyone for spending time with me on diodes and diode logic. But before you go, I'd like to leave you with an encouraging verse from the Holy Bible. It's James 1, verse 5. If any of you lack wisdom, let him ask of God, that giveth to all men liberally, and upbraideth not, and it shall be given him. All right, well, thank you very much, and take care.